It's our great pleasure to have Simon Knapen from Berkeley. He's going to tell us about a compact detector for eXotics at LHCb.
Hi, thanks for having me. So this is most of this work from last year, mostly with Baba Ligrov, Mikhail, and Dean. Baba is on the LHCb, so he's provided parental guidance for this thing. And there's a few results from upcoming work with a bunch of theorists where we try to flesh out a physics case for this thing a little bit better. So the motivation of long-lived particles, and this is something that you already know. Long-lived particles are very generic, especially in the static model. You have between, well, if you don't count the guys that we think are stable, about 30 orders of magnitude that are spanned in terms of lifetimes and over a variety of masses. And essentially, whenever you have a hierarchy of scales in the standard model, the W mass over the QCD scale, you end up generically with long-lived particles because you have an off-shell decay. Symmetries are another possibility. You see this sort of very rough trend of if you start decreasing the masses of these things, the lifetimes will get longer just because the hierarchy tends to grow. And so this is, so we're seeing many of these in the standard model, and so also in beyond the standard model, many of these models, you can probably just come up with 5 more that are not listed. Essentially, you also generically get separation of scales, and so it's not a surprise. Also in these models, very often only particles show up. Because you have such a wide range of masses and lifetimes, one single measurement or single experiment is not sufficient. You need a suite of measurements to have comprehensive coverage for all of these things. So this is a cartoon of what Atlas and CMS are currently doing. So you see there's a whole bunch of different channels they're looking at, a neutral particle decaying to a jet, for instance, or decaying to an invisible particle, and then something else is displaced, and you have things that are stable from the beginning, and so on and so on. And essentially, this is a huge parameter space, especially if you account for the fact that wherever these decays happen, the detector requires a completely different analysis, different background story, and so on. It's a very small community currently still in Atlas and CMS, but they made a huge amount of progress already, and the amount of people working on it is expanding. And so the general challenge is always where do the things that are already done, where do they break down? Because it's much more difficult to recast these things than you recast your sort of conventional Jetspot SUSY search or whatnot. And so there's a large community effort underway where there's some 500 people, a couple hundred people white paper with a lot of pages where this sort of will be fleshed out. And this should be out sometime in the late spring. Although we've said it before, so we'll see. But specifically, the challenges on the experimental side that comes with these sort of fall roughly in 3 categories, I think. So there's triggers. You need to find a way of getting these things on tape, especially if the decay occurs in the inner tracker, because the inner tracker is a very powerful instrument to reconstruct vertices and to look for displaced things. But you typically don't have access to it or to all of it on the trigger level because it's a relatively slow instrument, and you need to get the thing offline first, and then you can do the reconstruction. Backgrounds are, especially for theorists, a major issue because they're often rather low, but they are very subtle, especially if you start decreasing the masses of the long-lived particles. Things like front-street jets, cosmics, Goward backgrounds, all sorts of things that you can essentially only measure, very difficult to model coming in. In some cases, reconstruction is also an issue because you have this displaced object decaying in the detector, so you have to somehow reconstruct it with not the full information because the inner layers you don't have any hits, and without the impact parameter constraint that usually you require an object to point back to the primary vortex. So these are all complications. And so I threw this in. This is especially for Marcus. So in case there's any students in the room who somehow have not yet heard about this, if you have a confining hidden sector where the confinement scale is low compared to the masses of the vector-like quarks, you can have this sort of behavior where you pair produce one of these vector-like quirks, in this case as they're called, and if they go far enough, they start feeling the confining force and they come back and they start oscillating in this sort of funny pattern that I took from Marcus's paper in 2008. And so, especially with these oscillations are very large, that they look like regular tracks, and then there's a way of constraining them. If they're very small, it looks like a single track in the detector. You can also constrain them. But the intermediate regime, where they have centimeter-size oscillations, are very difficult because it seems like a very striking pattern, but there is essentially 7 free parameters in any such event. You have to keep in mind that a typical event has several thousands of unassociated hits from pilot vertices in each layer of the tracker. So digging this sort of thing out with a fit from all these parameters is essentially impossible. So we're trying to find a more general way of, without having to do a fit, digging this out of the background. And so the idea is essentially that because these things are produced with a negligible amount of angular momentum, a couple of units of h bar at most, and they're macroscopic objects, essentially their trajectories lay in a plane. So this is corrected a little bit by the B field of the detector, but you can show that as long as the Lorentz force is smaller than the string tension of this object, which is always the case if you have centimeter size oscillations, you don't wiggle the plane enough within the experimental resolution. So essentially the idea is to just look for pairs of hits in each layer that all nicely line up in a single plane. And once you have that, you know which hits correspond to your quirk candidate, and you can try to do, on this limited number of hits, you can try to do a fit. What you see here on this plot over here is this delta as parameter is essentially the thickness of this type of plane. So this is the RMS, the mean RMS separation of a hit towards the best fit plane. And the red and the purple are two colors of electrolyte quark benchmark. And this green is essentially the background you get from accidentally having unassociated pile of hits that accidentally form a plane like that. And if you cut roughly on like 0.01 centimeters for this RMS value, you find that with 300 inverse femtobarn, you have a handful of background events, and you still have like 70–80% signal acceptance. And so this is the only handle that we're using here. So once you have those few background events, if you're actually doing a fit through this, you can also kill those as well offline. And so essentially this is the sort of essence of what a reach for this type of thing is. These green, this green curve here is the current constraint from HPC searches. So this means that sorry, I should explain what's on the x-axis. So this is the mass of the quirk. This is the string tension essentially. So the string tension is very low over here. The trajectories are very wide, and a regular HPC search for just a charged particle traveling to the detector will essentially pick this up. If you start increasing the string tension, then this is no longer work. And the current best limits are from essentially monojets, because you don't reconstruct this thing, it looks like there's missing momentum somewhere. But those constraints are very poor because of the systematic uncertainties associated with the backgrounds and the large backgrounds from diagnosing production of this sort of thing. So essentially two colored lines are for 3 and 5 events essentially the reach you would get using this type of technique. Where this hole is essentially just due to our limited computing power, because we make some assumption that the hits have to be rather close to each other when we start the algorithm, just to speed up the things a little bit. But with a bit more clever coding and more computing resources, you could also fill it out. And if you go up here, the hits start merging, and then there's a different search needs to kick in. So I have literally an entire talk in my backup slides about this. If anyone wants, we can look at that later. So the main topic of this talk is related to light long-lived particles and how to essentially add an additional detection system to the LHC infrastructure to look for these things, mainly because of backgrounds that are essentially irreducible at LHCs. And the reason why that is this is a sort of a cross-section of the CMS detector with the inner tracker, the eCol, and the hadronic colorimeter, and muon chambers over here. And so the cartoon version of what a long-lived particle search would look like is you look for a particle which travels all the way to the muon chamber and decays over here, and you're trying to reconstruct like a vertex in the muon chamber. Now the issue with that is if you go low enough in mass, there's a lot of backgrounds for this sort of stuff. And so the main reason why you have hope in the first place is because the hadronic colorimeter is made of very heavy stuff. So in the case of the CMS, in particular, this is about like 1 million retired Navy shells from World War II from Russia that they like, well, we don't need those things anymore, you can melt them and make a colorimeter out of it. So this thing is very heavy, and you roughly have about 5.1 nuclear interaction lengths or something. Which means that a typical hadron has a probability of like 1 in 1,000 or so to make it from the interaction point all the way to the muon chamber. But if you remember that we make roughly 10 to the 9 kiloohms per second at the LHC, that's still a huge amount of hadrons that make it through over here. You don't have mass measurement anymore here because there's no other detector on that side to measure the actual energy. So all of these things provide a background for light long-lived particles. So your only handle at this point, leading order, is counting on the number of tracks in the muon chamber that you're constructing. But if that number is low, essentially you're in trouble. So there is a couple of complementary detectors that partially address those problems already. So LHCb in particular is very nice, especially for lighter, somewhat shorter, longer particles, because they have fantastic vertex resolution. So they can reject some of these backgrounds by having really good vertex resolution, mainly because their vertex locator here, the velo, there is no magnetic field there. So there's no curving of the tracks, which makes their pointing resolution quite a bit better. They also
can I go back to the thing a little bit? So I haven't really thought about this for light particles, but if you have a very energetic light particle, isn't it? I would think that most of these hadrons, the energy per particle should be pretty small, I would guess. Maybe that's incorrect. Compared to like if you produced a light particle from a hard process, it would have a lot more energy and therefore deposit more energy. I mean,
but they don't deposit energy because the decay products leave the muon chamber. There's no more calorimeter here.
But somehow
so
you
just
can't
measure the tracks. That's essentially it.
Yeah, but somehow you can't use like opening angles. You don't get any energy measurement of the decay products. That's what you're telling me.
Not really. I mean, you can use opening angles, but they depend on the boost, right? And so you can't really fully disentangle them. Your best discriminator is the number of tracks, because like suppose you have like a 50 GeV particle decaying to 2 quarks, right? So this thing's going to hadronize, it's going to shower a little bit, it's going to make 6, 7 tracks, right? And the standard model does not have any particles that make that many tracks.
So when you say light, maybe I didn't know what you meant by light. So what do you have in mind?
Define it more precisely, but like let's say something below 10, 20 GeV.
Below 20.
The number of tracks essentially typically is less than 4. Which is a model-dependent statement.
So because it's still somewhat heavier than a QCD hadron, that's what you're...
Yes. And again, because the main handle we have is the number of tracks that we're making. So suppose I have a heavier particle which always decays to 2 leptons. Leptons are actually bad for this kind of thing. Because it's much more difficult to reject backgrounds than it would decay to jets.
Yeah. Okay.
And essentially what you need to do is interquire 2 of them on opposite sides of the detector in order to get rid of the backgrounds. Cosmics and so on also become an issue. But LHCb, especially if the lifetime is short and you can reconstruct in this first part of the detector, they have really, really great resolution. And they can do quite well. And I'll show a few examples of that in a minute. Other experiments that currently exist or are being proposed that are designed to look for long-lived particles are beam-bend experiments, where you just essentially have like a proton beam, you smack it into a target and you see what comes out on the other side. And because of the boost of the entire system, you have a very nice geometric acceptance for things that come out on the other side. And you can build like a very sort of elongated but somewhat narrow detector for it. The downside of this sort of thing is, of course, that you have a low center of mass energy, and things like exotic Higgs decays, exotic Z decays are essentially out of the question. We can't do that, at least not with existing facilities.
Remind me, what's the center of mass energy at LHCb?
It's the same as at Atlas and CMS. It's the same D.
Really
so it's 13 T.
I thought it's not asymmetric.
No, the detector is asymmetric, but the beams are just proton. Yeah. They can do proton lead, but it's a different.
Its luminosity is lower, right?
It's a factor of 10 lower than the CMS. So they have about 5% of arc right now. They'll go up to 300 eventually. And so then there's the final option, which is a more recent thing, is where you consider a shielded detector at the LHC. Essentially what that does is you try to put it near one of your high luminosity interaction points for the LHC beam, and you're putting in some shielding, and so you benefit from the high square root of S because you put it somewhat centrally. But the price you pay is you sacrifice the geometric acceptance because you can't build a detector that's 4 pi just because of space restrictions. So the first example of this is some of you may have heard of, is this Fiducial proposal. Essentially, this is the Atlas or CMS interaction point, and they want to build something of the size of an airplane hangar on top of Atlas and CMS, or CMS, not both, with some tracking layers in the surface, and they're looking for a long-lived particle that's coming through and decays inside the detector. And the backgrounds, the hadronic stuff that I talked about will get stopped in the Earth, essentially, so we're using it as a shield. So what we're proposing is a much smaller scale experiment. Essentially, in the LHCb cavern, there's a space available that we can use to look for this type of particles, and we can shield it fully. And then our reach is not as good as something like Fiducial, but it's a few orders of magnitude smaller detector, and the logistics is a lot easier for this kind of thing. And then I just want to mention quickly Millikan also, which is a small experiment that will sit in the drainage gallery above CMS, is looking specifically for newly charged particles. But they have a very specific dedicated physics case. Alright, so this is sort of my quick overview with a lot of caveats on where all these different experiments sit in this very simplified phase space of long-lived particles. So if the mass is high, where high depends on the final state, it depends on the detector and whatnot, so this is sort of a fuzzy boundary. Atlas and CMS are doing really well because they can reject backgrounds very efficiently and have really good reach for things, let's say, about 50 to 60 GeV in mass, especially the decay hadronically. And this is sort of independent on the lifetime to some extent. For shorter lifetimes, there's trigger issues, but we can, for now, switch what we can run. LHCb does really well for long-lived particles that are relatively short-lived, like the order of several centimeters, less than a meter essentially, and they can go to rather low masses of the order of hundreds of MeVs because it has exquisite vortex resolution. And then finally, if you want to go larger lifetimes, LHCb does no longer work because particles decay outside the detector essentially. And then there's these two sort of larger scale detectors that you need to shield separately, or with the beam dump proposals, but they only work for low energy portals, so things like neutrino portals or light scale, which makes it the Higgs, that kind of thing, but not for like a direct exotic Higgs decay. And so this talk is, I'm going to focus on this proposal for detector LHCb. So this is what LHCb can already do. So they're looking for scalars mixing with the Higgs below the B threshold, essentially B2KX.
Sorry, actually, can you?
Yeah.
I didn't get that the distinction. What's the basic distinction between what, like SHIP et al. Are sensitive to and you? I mean, I thought it's not just. What is there besides lifetime? Is it just somewhat heavier masses? Is that the point?
So there's a third axis which I need to project on here. So I didn't explain it very carefully, which is the center of mass energy you need to produce it. So suppose that you have a long-lived particle which you make an exotic Higgs decays.
Oh, I see.
It requires you to first produce a Higgs and then you can see it.
I got it.
Which is something that these guys cannot do.
Okay.
So there isn't some
So
sense
stuff that's coming, roughly I can think of it as stuff that's coming from decays of heavy.
Correct. Yes. Now we'll see that we can also eat into the parameter space of these guys. Essentially, we can produce to a low energy portal.
Right,
Yeah.
because they can, to some extent, in principle, they should be able to make that up with luminosity, right? With the beam dump, you can get it.
Yeah, I mean, it depends on how much,
luminosity.
especially for SHIP, it depends on how much money you're willing to spend.
Yeah.
So we're talking like a $400 to $500 million experiment.
Mhm.
So this is, so they will do better than everybody else in this regime, but like depends on how much money you have and willing to throw at this.
Yeah.
Yeah.
Okay.
All right, so this is obviously a bit of a cartoon. I mean, there's lots of variables that go into this, but this is how I project it down, just to get a sense of what this looks like. LHCb already does a bunch of very nice things. So they can look for dark photons, they can look for scalars using the Higgs. We'll discuss that search in a bit. And there's this paper from last year by Lucen and friends with this very nice hidden valley search, we're proposing a hidden value search for things like neutral naturalness at LHCb. I think the collaboration is looking at it now to implement that sort of thing. So this in particular is if you have a scalar mixing with the Higgs, below the B threshold it can decay to, like the B meson can decay to a K1 or a K1 and this extra scalar. This is the constraints that can be set. These green constraints are very null opinions, which should essentially be like for this purpose. They have something very specific thing in mind at the time. So this is the LHCb cavern, which presumably most of you have never seen before. I haven't really seen this picture before, and I just came across it. So I'll let me walk through it. So this horizontal, vertical line here is the beam line. So the protons coming in from both sides and interact and collide here at this blue dot, which is put on the side of the cavern. And this triangle on this side is the LHCb detector. If you move to the left, there's some empty space over here. There's a radiation shield of 3 meters worth of concrete that sits over here. This rectangle is their data acquisition. So this is where the data goes. They process it and then send it to the surface. And this last rectangle here is the corpse of Delphi. So after they were done with Delphi, we used to sit over here to sort of shove it aside and like, well, it's a tourist attraction now, you can go see it. It just sits there. But the key point is, for our purposes, that the data acquisition in the next upgrade, which is happening in 2019, starts in 2019, will be moved to the surface because they want to do their entire data analysis and calibration online, and they need a bigger computing farm. There's no space over here, so they're going to literally pipe all their data through an optic cable to the surface and just do everything in real time. But that means that there is some space that becomes available over here, which already has a radiation shield in front of it. And so the proposal is to instrument the space with some very basic tracking layers. And in addition, add a shield roughly 4 meters worth of lead close to the interaction point to essentially get rid of the remaining hadrons that are not yet stopped just by this 3 meters worth of concrete. And so then if you have a long wave particle that's produced at the interaction point, it travels through all the shield and then it decays inside this box over here, and you can resolve the decay products. And so that's essentially the basic idea. It's really opportunity driven because there's a space here that will become available. You don't need to build any new buildings or anything like that. You can just use this.
If it weren't for the space, you would rather build this next to Atlas or CMS if space wasn't an issue.
Correct. If they have the space,
because you have better luminosity.
You have more luminosity, yes. But you have to work what you have. There's no, to my knowledge, and anyone I've talked to, there's no real space there. There is some space in like very forward tunnels, right? So you have there's some stuff there, and there's one other proposal that wants to make use of that. But if you go to very high eta, then you lose the benefit that you can in terms of like Higgs decays and things like that. So you want to be really sort of central, and that real estate is very valuable for them. They fill it up entirely with their detector. So it's not really any space. Yeah. So what do we have in mind, right? So this is a cartoon of like the sort of first sort of layout, or one possible layout that you could envision. And so this is not set in stone in any way. First, so we have a 10 by 10 by 10.
Sorry, but you couldn't put it on top, right? Top of above Atlas or CMS.
Well, they're like,
you have to.
you mean on the surface or in the cavern?
Secure it. Well, I mean, there's like.
Oh, you want to suspend it in the shaft?
Yeah.
Yeah, people have mentioned that. It looks kind of nuts because, like, if it somehow falls,
if it falls,
you're not really.
I know, but
you're in exceptionally bad shape.
You could get it in and out, you know.
Yeah. So people have asked us like, oh, can you suspend it in the shaft? I'm like, well, I'm not qualified to answer. You need to ask the engineers, but like, they're not,
You put a little net under it, to catch it.
Well, there actually is a net. There is actually a net in case you drop a screwdriver or something like that.
Yeah.
So it will catch a screwdriver, but whether it will catch a multi-ton detector, it's highly unclear. Yeah, so in principle that's an option, but then you also need to somehow have shielding. So you need to suspend that somehow as well. It needs to be able to take it out in and out. So it's not something that
I mean, they got big chunks of the detector in now, so they have some kind of crane.
Oh, they have obviously a crane, but the thing is also that the shaft is like, it's big, but it's not, you know, in terms of geometric acceptance, it's not that much bigger than what we have here.
The big crane was taken away.
The big, oh, I see, so, okay. Anyway,
Oh, yeah,
it's,
yeah.
but no, I mean, it seems like it might not be worth it.
Yeah.
Sorry, go ahead.
Yeah, so the size of this thing that we have in mind is something like 10 by 10 by 10 meters, which for the location that we're exploring is about 1 to 2% of geometric acceptance. So the geometric coverage is not great, but it's a relatively small volume compared to something like Tuzla, which is the size of an IKEA. So what we propose to do is essentially you instrument all the surfaces. Because it's a relatively small detector, you want to reduce the loss of like particles that are going out at wide angles and go through the sideways or even to the back. So you want to instrument every surface, which in this case, you know, these red lines represent 6 layers of RBC each. You could probably do it less, but that's just what we picked for a first simulation. And then we have a bunch of tracking stations in the center also with 3 layers of tracking stations each. And so this is just to reduce the distance to the first tracked point so that you have a better vertex resolution. So if you track for a very long distance before you measure if you travel a very long distance before you measure your first hit, you have a very lousy resolution where the vertex really is. This is one of the issues that this level eventually have to deal with. And I think this is exactly what I said. So we instrument all the sides to recover low boost particles. And these things are essentially there to make sure you have a decent vertex resolution, the order of 5 centimeters, something like that, rather than meters.
You're just saying you want as much track in your detector as possible, right? So you
For a
have
given price.
Yeah, so you
Yes.
have, right, everything for a given price.
Yeah, so that's right.
Yeah,
Yeah. So the real design will be very different from this. Presumably a little more minimal. This is quantifying a little bit what I just said. So essentially, the take home is that, you know, this vertex resolution. If we decay inside the tracker that we have in mind with this layout, this is sort of the typical vertex reconstruction efficiencies, where we require that each hit has at least 6. Each track has at least 6 hits, and we require that the first hits don't merge for the 2 tracks because then it looks like a conversion. And that's essentially if the boost gets very high, so very light particles. This is why you start losing a little bit of efficiency because the tracks are too close to each other. Essentially.
This is out of the events that somehow
Out of the
hit your
events
detector,
that would decay
whatever
in the
that
detector. This is the efficiency. Just to give you a sense that, you know, this is 101 efficiency with this type of layout. Yeah. And I think this is what I just described. And yeah, this is a small opening angle. So if you go too light, then there's a bit of loss because of the opening angle. But these are sort of, yeah, this depends on the design of the detector. There's a few things you can do with this thing as well. So it's relatively close to LHCb, about 4 branch crossings away, which means that there's time enough. They buffer more than 4 events. So this thing would be integrated in the LHCb layout and would be part of the trigger event reconstruction, the whole thing. So it's essentially becomes a sub-detector of LHCb. And you can look at this together with the primary and the main detector. Okay, this is just saying that we're still exploring, and like there is the time projection chamber is not entirely off the table, something along the lines of NOVA, which will give you a better tracking resolution potentially for your mark. But it's to be seen.
Sorry, remind me what a time projection chamber is? Is that the wire and gas thing?
You know, it's like a tank of liquid essentially, and you're essentially you have modules where you're producing ionization energy and you drift it up, and then you reconstruct that way. This only works for very low occupancy detectors, which is what this is, because we're shielding it exactly such that we expect very low occupancy. So you couldn't do this at Atlas and CMS because the thing would never actually read out anything. It's essentially the same as like something like xenon or rocks, but less fancy. We don't need that explicit energy resolution as they have. One neat thing that may work, and so this requires further simulation, is suppose you have a longer particle which decays after the lead shield, but before the concrete shield, and it decays to muons. It will just penetrate through the concrete, and you could try to actually reconstruct the vertex outside the volume of the detector. So this, of course, gives you more errors on the vertex reconstruction. It's a riskless study whether this is really feasible. But if it is, then this essentially increases your Fiducial volume for this type of decay, where you have muons in the final state. Alright, so this is what it can in principle do, and in order to convince you that this is useful in any way, I need to tell you what the backgrounds are and how we think that we can get rid of these things. So the first background are just muons coming from the primary interaction point that scatter on air in this box, because you're not going to pull this thing back in. That's not really feasible. There's just air in there. You could generate tracks that way. And so this is a simulation. This is the initial muon flux which we get from PITIA and then data at low energies, which we then pull through JM4 simulation. This is sort of the residual muon spectrum, which, as you can see, there's a bit of statistical noise on here. But the point is that essentially the hardest muon in the LHC that goes through this amount of shielding is in the order of like 11 to 12 GeV. All the others get slowed down substantially. And so you find that you have roughly 10 to the 7 events if you would not have any vetoes, where the muon would come through and would scatter on air. But you have 6 layers of detectors in the front over here. We also envision having some simulating layers in the shield. I'll explain in a second why that is. And so with all these redundant instrumentation, a rejection of 10 to the minus 7 is relatively easy.
So which 10 to the 7 events per what?
For the entire lifetime of the experiment.
Oh, which is?
For like 10 years.
10 years.
So this is muons. So muons we can deal with because we can veto them.
Is that a lot? Is 10 to the 7 a lot? I mean, if in 10 years, that's 1 every 10 seconds or something. Is that really a lot?
Yeah, that's not, as far as the readout time of these things is of the order of microseconds or so.
I mean,
So
it
it's not
depends
like
on
it's
your
such a-
signal rates, I'm just saying, compared to your signal rates.
Yeah, but if we would not get rid of this background, this would be a disaster.
That's what I'm trying to
Yes.
understand.
But you need to veto these things.
Because you're imagining signals where you get just a few events a year or something like
Yeah,
that?
or a few events of the lifetime of the experiment.
Okay.
So you need to veto these things. And a single detector can never get 10 to the minus 7 rejection, but if you have multiple redundant layers, each of them is like 1% efficient or something. If you have 6 of them, then that's enough to, because they're unrelated to each other, of course. You can veto these events. So a muon veto of 10 to the 7 with a number of redundant layers is something that's really not complicated. At least if they're spread out over this amount of time. So you don't need a very fast readout. Hadrons are other backgrounds. So the most straightforward one is where you have an irreducible background where there's just like a K-long traveling through and decaying over here. And so those we got rid of by just putting an outlet over here to just absorb all the hadrons, all the neutrons and the K-longs, so that we get rid of those guys. Another possibility is if there's a muon hitting the lead over here, creating some K-long, and then going through the muon bends off and you lose the muon. That's another background. Again, by just having a lead, you can also attenuate these things. There is a reducible background where if you have a muon, again, muons will go all the way through to the lead shield, they don't care. And they may hit in the concrete, create some K-longs, create some neutrons, and these things provide backgrounds for you. And so this is why we have an active muon veto inside the shield, where you're trying to tag the events where the muon passed through, and you say, okay, this one had a muon in it, so if you see something in the detector over here, this is probably a secondary from this primary muon. And so you find that in order to, if you do the math, you need roughly 4.5 meters worth of lead. If you use tungsten, it's going to be about 4 to 3.5 meters or something. You want this shield with this active veto here somewhere, 4/5 in this lead shield. That's the optimal location to get rid of all these backgrounds. It's just some calculation we can do. This is the numbers for this are over here. So we have only the calculation where you do propagation could matter, but the more precise thing to do is to run a GM4 simulation. So these are the results over here. The kinetic energy of the particles versus the number of events. And so there's the blue are the kilowatts and the green are the neutrons, where it's hard to see, but the fainter line are the ones that can be vetoed with the active muon veto. In any case, the main backgrounds are going to be neutrons. So we find that with this amount of shielding, there is about 7 neutrons over the lifetime of the experiment that make it into the detector volume. They have on atmospheric pressure, they have a scattering probability of a couple percent. So this is roughly 1 background event, essentially less than 1 background event for the lifetime of the experiment. The reducible ones there's a lot more of them. There's like 50,000 that we estimate. So you need your active veto to veto muons to 10⁻⁵ precision, which again a single layer will not do, but a few redundant layers of scintillator.
What are your, for the same particle, neutron, anti-neutron, what's the distinction between the irreducible and the reducible ones?
So the irreducible one is just you make a neutron at the interaction point, and it just travels through the lead, and it just makes it into the detector.
Oh, right.
Okay? The reducible one is that you made a muon, and the muon hits the concrete somewhere, it creates a neutron, and because it's almost at the end of the shield, it's not attenuated anymore, it makes it into the box. So that's this scenario over here. And so those you have to veto the primary muon to get rid of these backgrounds. Essentially. Does that clarify? And yeah, you can check that neutrinos from the interaction. The secondary neutrinos are totally negligible. Yeah, I think I said everything that's in this slide. And your final background is neutrinos from the primary interaction point. These are very difficult to model because they all come essentially from pions. So you have a bunch of pions, you make them, they get stopped in the detector material, in the shield, whatever, and they come to almost to rest, and then they decay to neutrinos. Or they decay in a decay chain which has neutrinos in it. And so you need to really model the cavern and the detector, which is something that's exceptionally hard to do with what we have right now. But we make some very, very, very conservative cuts, and we end up with like about 3 events for the lifetime of the experiment. And I expect that this is several orders of magnitude too conservative. So for instance, Methuselah has done the same exercise, and they used the full CMS simulation for this. And they found a few orders of magnitude less events than what we had. So I think we can be confident in this. That's eventually not going to be an issue.
So you said this is the final background, and we don't have to worry about cosmics at all?
Cosmics will come in from this side.
Yeah.
And so if you have enough layers, you can essentially figure out what
But
direction
even
to
some
travel.
weird scattering events like cosmics hitting your shielding and scattering, I mean, if you're talking about a few events in 10 years,
Yeah.
you don't have to worry about rare things like
Well,
that.
the cosmic rays are not so much of an issue because we have this huge amount of soil in between us and the sky. But Methuselah has to worry about this a lot. They have 10 to the 15 cosmics over the lifetime of the experiment. We have many, many orders of magnitude less. Essentially because the hardest cosmic that can come through has to be a 60 GeV muon, which is a fairly hard muon.
Unless you
And so
put it in the shaft of those things.
Yeah, so if you put so actually you can look at the cosmic ray. If you look at the cosmic ray map of CMS, right, there is a bright spot on one of the sides, and it's literally the shaft. So you can see the shaft
Right.
if you map out the cosmic rays. Yes. But the cosmic rays that are mainly a problem would be the ones that come horizontally. They travel to a huge amount of Earth before they get to you,
Right.
and so they're essentially all attenuated. We don't need to worry
So,
about it. When we check these things, and so they're sub-dominant to muons coming from the interaction.
and for just like radiation, it's just too low energy, is that the point? So like
Yes.
just your cavern walls are radiating, or everything is radiating, but
Yeah, so essentially what you need is 2 charged tracks, right? So we're not looking for a small amount of energy deposition.
yeah.
So it's not like a dark matter experiment where you need to get rid of radioactivity.
Right.
Radioactivity, by definition, is not enough to shatter another nucleus and then make it split into muons or whatever. So you need like at least a 4 or 5 GeV particle to work through, which is not something that you get from cavern backgrounds. Yeah. All right. So what do you do with this thing? So I'm going to show you 2 benchmark models which we calculate the reach for. One is where the light scalar mixing with the Higgs, and you get this beam meson decay into any strange meson, and then this new particle phi, which is the thing mixing with the Higgs. And so what's nice is that both the production angle and the lifetime I know just, the production rate, sorry, and the lifetime are just set by the mixing angle of the Higgs particle, and you have a very predictive model. We also looked at this dark photon model where this is Higgs decaying to 2 dark photons decaying displaced. So this is a 2-parameter model where 1 parameter controls the production, the other parameter controls the lifetime. So this is what the B decay looks like. So this is the usual penguin diagram. You have W in the loop. You couple to the top quark by mixing with the Higgs. And this thing decays this way. But this is how you produce it. And the S, of course, aggregates as well. The issue with this model on the theory side is that there's a huge uncertainty on the lifetime. So you see the different thresholds. So this is the muon threshold kicking in. There's a 1 GeV where the rho and the sigma and so on come in. And you see the charm threshold and so on. But especially this regime between GeV and 3, 4 GeV, there's a very large uncertainty still over the lifetime of this thing. And so you have to be, when you compare different experiments, you have to make sure everyone makes the same assumptions. Especially SHIP was making very different assumptions from everybody else. And so we took great care to recast their reach into the model that we're choosing, which is the blue line is what we're picking because we think this meson contribution around 1 GeV is very reasonable. It's not really reasonable to not include that. So once you do all that exercise, this is the type of reach you get. So this green curve, so this is the mass of your scalar versus the mixing angle. This green curve is the current existing LHCb limit that I mentioned earlier in the talk. And here's our estimate of what this would look like with the full luminosity, the full data set of 300 inverse femtobarn. Blue charm, the charm band is like some Alpine experiment from the 80s. And the blue line over here is what the CODEX-b reach would be, where the dashed line includes the tracking resolution that I calculated, showed you earlier. So this is an estimate of what this could be. Well, blue is if you just assume 100% tracking efficiency. The dot dashed line is a very optimistic scenario where maybe you could extend the luminosity to the inverse Aldebaran line of the inverse femtobarn. This is somewhat unlikely to happen. But this just gives you a sense of what would happen if you would do that. The dashed line is SHIP, and the yellow line is what Methuselah can do. And you see we're sitting sort of in the middle between those two. And so they both do better than us, but they're also 2 orders of magnitude more expensive. So there's a bit of a physics for money kind of trade-off.
What is this gap between the green curves?
This gap over here, I think this is going to be the epsilon. This is the epsilon, I think, if I recall correctly, because you just have so many muons just coming from. They're looking for that muon resonance, but the epsilon sits there, and the background is just you can't really set up with it. Yeah, so whenever they have these sort of dips, the smaller ones are probably statistics, but then this is definitely like a meson. Looking at the mass is probably the epsilon. Yeah. This is the reach for one of these exotic Higgs decay. I have a Higgs decaying to 2 long-wave particles, which is decayed to 2 other particles. Or again, here you see the lifetime of this particle versus the branching ratio of the Higgs for half a GeV and 10 GeV. So the solid, the shaded bands are projections on what the sensitivity of something like Atlas and CMS would be. Where if you're light enough, the backgrounds to look for a single vertex are essentially prohibitive. You can't set any limit whatsoever. So what they're doing for this search is they're looking for 2 different long-wave particles on opposite sides of the detector. And so that means that if you increase the lifetime, you lose quadratically rather than linearly. And so that's why you're turning off much faster than what CODEX-b would do. So this is the blue line. The solid line here is the CODEX-b reach, assuming that we cannot do the tracking of the muons through the concrete wall. If you assume we can also do the muons through the wall, then the reach gets a little bit better. This dotted line over here is what Methuselah is capable of, and so on a given mass point is roughly 2 orders of magnitude, just because they have a factor of 10 more acceptance because they're bigger, and they have a factor of 10 more luminosity. Essentially, that's what drives his estimate. On this side it's the same thing, except that, so this is again the double displaced vertex search at Atlas. This is a proposed search for a single displaced vertex, and you see it turns off slower at long lifetimes. And so here, something like CODEX and the existing Atlas is much closer to each other. So this gives you a sense of what masses. So if you go much higher mass than 10 GeV, probably Atlas and CMS will be fine, and you don't need this particular type of detector. So this is really a proposal for a sort of lower lifetime, below 10, 20 GeV or so. Yeah. So again, the Tuzla can do better than anybody else, but again, at the expense of more tracking surface, essentially. Okay.
So it really falls off. Yeah, it falls off. I mean, sorry. I guess Atlas and CMS kick in at a relatively low mass already, near 10 GeV or something.
Yes.
What about lower masses? How low can you go?
We can go as low as until we can essentially, it depends on the boost of the particle, right? So for the Higgs particle, where you have 100, in the case of two guys, so there's like a 60 GeV each, and then you have a half a GeV particle.
Yeah.
That's roughly as low as we can go, because if you go lower, then they start to be really collimated. It becomes difficult to disentangle, because we don't have a magnetic field. That's not really possible. So this is probably like roughly as low as you can go, or maybe like 250, 300 MeV. But yeah, much lower than that is probably not happening. At least not for this production portal. Right? If you produce it with much less boost, the opening angle is larger, and then you can go lower than that. All right, and this one is some sense for some of the locals. So you can map this previous projection onto some neutral naturalness benchmark, right, where you have a dark sector with, which consists of dark blue balls, and it talks to us through Higgs mixing. So you have a Higgs portal over here, where the dark Higgs essentially mixes with ours, and this is how the blue balls end up decaying. And so the main point here to remember is that the lifetime of these things, because it's a higher dimensional operator, it scales like the 7 power, the inverse 7 power of the mass. So that means if you go lower in mass, the lifetime shoots up very, very rapidly. And so this means that Atlas and CMS are losing twice. On the one hand, if you go lower in mass, their backgrounds go up. And on the other hand, their acceptance for their double vertex search is dying off very, very fast because the lifetime becomes so fast very quickly. So this red shaded region over here is sort of an estimate of what Atlas would be able to exclude. And then CODEX-b sits in this blue range over here. The Tuzla level, we have a tiny little bit more sensitivity on this side. But because the lifetime goes so fast, the mass shouldn't be much difference. Alright, and so then finally, to wrap up, essentially, if you suppose you would see something, right? So you could ask, okay, what do I learn from this, right? Because all I have is tracks. I don't have a colorimeter, I don't have a magnetic field, or nothing, right? It turns out that you can do an approximate mass measurement by looking at the opening angle, something that you alluded on earlier. You can use this for your signal, essentially. So essentially, in the limit where both particles are moving relativistically, the boost of the incoming guy decaying directly correlates to the angle that we're measuring. This is what you're seeing over here for these different benchmarks with the tracking layout that we assumed, which is some preliminary estimates. You see the resolution on the beta gamma parameter of the mother particle that we can get. And so this is like for all of these benchmarks, the two that I discussed for different mass points, this is always in the order of like a % level resolution that you can get just from how well you can track these things. And so this again depends on how much tracking layers you have, what your vertex resolution is. So for the example that we use, this is quite good. And you can try to, if you now assume a particular production mode, you can try to turn this into a mass measurement. This is what this looks like for these two different benchmarks.
Is there a sort of a consistency check? I mean, if you can you just go back? So you can measure. You're not anywhere near the limit of your angular resolution, right? So I mean, you could actually experimentally see this distribution, or no?
Well, this is your, yeah, in principle, yes, but this is like, you know, the error on your, this is what you simulate to be the error on your reconstruction of the boost, right?
Right, so that's.
So this
so I
is
guess what
roughly
I'm
an
asking
estimate of the
is-
smearing, yeah.
Yeah, I guess, yeah, that's not the right, so what I'm asking is that do you literally see the angular distribution? Because that's,
That's my next slide.
oh, okay.
Yes. So what you would do to calibrate this, right? So you would remove some of your shielding, right? And you would look at something like K-longs. You let some K-longs through. You know what mass they are. You know what boost they typically come with, and you can calibrate your energy resolution using that. And then once you do the measurement, you put the lead back. But this is, yeah, I hope this is maybe answering your question. So as a function of the reconstructed boost, which is a proxy for the angle that you're measuring, it's a one-to-one map. You can reconstruct for different mass points, there's a different distribution that's happening, right? And so if you're assuming a particular production mechanism, like either the B decay or the Higgs decay, you can get this different peaks out of it. So you can get some very rough mass measurement, as should you see some sort of excess. And then of course, you know, once you convince yourself you're seeing something, you expand your detector, you put colorimetry, whatnot. But for first pass, you want to spend as little money as you can, and so this is what you can do. It is in principle possible, this is only using spatial information, to also use some timing information if you have very fast detectors. And so this is assuming 100 picosecond timing or 50 picosecond timing. You include some time of flight information. And this is for the Higgs benchmark. You see roughly how much your resolution improves, so you can do a bit better.
Sorry, what am I supposed to look at here?
Well, you're supposed to look at these peaks that are becoming more and more separated if I have a better timing resolution.
Oh, I see.
Yeah.
Okay.
So this is for the B decay, where, you know,
Right.
in the previous, if you don't have timing, like they're kind of crappy, like they're overlapping a lot, because they all come with roughly the same boost, right? But if you have timing, then there's a bit better, you have a bit better
Yeah.
handle. So you can distinguish like a half a GeV from a 2 GeV guy, for example. Yeah. All right, and then to wrap up, I'll tell you what is ongoing and how we're moving forward with this. So we're working on more benchmarks, so some of which are in the backup slides, heavy neutral leptons, axion-like particles, that kind of thing, that you can also see with this type of detector. That's on the theory side. On the experimental side, LHCb is installing, or they have installed this thing here. It's a bit hard to see on the slides, but essentially it's like 2 plates of scintillators and phototubes to it. This is now installed, or will be installed soon, in the cavern behind the radiation shield to measure the background, the fluxes of background particles coming through, essentially to calibrate the overall normalization of the J-on simulation, which has some theory uncertainties to it. They're working on different detector layouts, and we're hoping to have some sort of concrete proposal for a funding agency sometime by the end of the year. The timeline for this sort of thing is, as I said, the data, we're now here in 2018, beginning of 2018. The second long shutdown will happen essentially at the end of the year for 2 years. This is when the data acquisition will move to the surface, when the space becomes available. So it's possible that we'll try to install like a small prototype for 1 by 1 meter or something like that. But the real installation, if this goes forward, would be in the third long shutdown in 2024, essentially, so that you're ready to take data for the high luminosity LHC. I think that's all I have. So essentially, quirks are hard, but if you look for planes, you can sniff these guys out as well. And then for light long-wave particles, CODEX-b style detector can be integrated entirely in the LHCb infrastructure, in the readout, everything. You can do now Reconstruction, and it would expand the reach of the LHC for long-wave particles with a relatively small instrument compared to other components. All right, I think that's all I have for this.
Any questions, Simon?
Someone besides you.
very clear talk then. That was thanks, Simon.